This webcast talks about Worksheet 2E, where we are using the equations of motion to solve some quantitative problems that involve constant velocity. So I want to look at problem 11 here. So this is talking about a train that starts at position 960 meters and moves at a constant speed of 54 meters per second in the negative direction. Part A asks me to write an equation of motion for this train. So equation of motion is like a physics equation, right? I leave my two variables, which are position and elapsed time, and I fill in the velocity and the initial position. In this case, the velocity has to be negative because the sign of the velocity has to match the direction of motion. And they're telling me this train is moving in the negative direction. Okay, so I take its speed and I put a negative sign on it. Its velocity is negative 54 meters per second, and its initial position was 960 meters. Question B says, what is the displacement after the train has been moving for 2.5 minutes? This is a good question, to remember and to note and review again, because it's asking us to be very clear about the difference between position, which is x, and displacement, which is delta x. So this question is asking me for displacement. And the common equation that we've used so many places that involves displacement is that the equation that gives us average velocity. Average velocity is displacement divided by time, or if I shift that around, displacement equals velocity times time. Well, I know the velocity. I just used it to write my physics equation. It's negative 54 meters per second, and they gave me the time of 2.5 minutes. Now, before I can multiply these two things together, I have a small issue of mixed units because my velocity is in meters per second, and they gave me the time in minutes. But it's easy enough. I'm going to just convert minutes to seconds right here, and then I can solve and find that the displacement of the train would be negative 8,100 meters. The negative is important because it tells me that the train was moved 8,100 meters in the negative direction. Question C says, what is the train's position after 2.5 minutes? And there are actually two ways that I could solve this, but I have chosen to write it by using the definition of displacement. Displacement is final position minus initial position. In part B, we found the displacement after 2.5 minutes. And so I know the delta x, I know the initial position, because they gave that to me in the problem, and I could solve for the final position and find that it would be negative 7,140 meters. The alternative way to do this problem, which I guess I didn't write down, I could have used my equation of motion and solved for x. Right? I could have plugged the 2.5 minutes, although I would have had to converted them to seconds. But if I converted that 2.5 minutes into seconds, I could have plugged that amount of time in for the delta t and solved my physics equation, and I would have gotten exactly the same answer. And then question D says, how long will it take the train to reach a position of 10 meters? Again, this is a great place to use that equation of motion. But what I'm trying to solve for here is the delta x, the delta t, not the position. I know the position I'm looking for, it's 10 meters. So I'll plug 10 in for the variable x, and then I solve that equation for delta t, and I find that it would take 17.593 seconds. Let me solve one other problem in this video for you. Let's go down to number 13. And this is a situation where we want to find the time and the position when two objects pass each other. And so here we've got a situation with an amusement park, and you know, a lot of times they have trains that take you back and forth from the parking area, which may be a long way away, to the gates of the park. And so here it says that there are two trains. They're initially 240 meters apart, but train A is moving at a velocity of 1.7 meters from the gate, which is at the origin, to the parking area, which is at 240 meters. And train B is moving at 2.1 meters per second from the parking area toward the gate. Gosh, I'm starting to get confused, so I need a little bit of a diagram, because I have to figure out which one of these is going in the positive direction and which one's going in the negative direction. The gate is the origin, the parking area is at position 240. So train A, which is going from the gate to the parking area, is going in the positive direction. Train B, which is going from the parking area back to the gate, is moving in the negative direction. Okay, so my first step is to write equations of motion for both trains. Since train A is starting at the gate, its initial position is 0, and I don't need to write that in my equation. Train B is starting at a position of 240 meters, but I need to be sure to write its velocity with a negative sign because it's moving in the negative direction. Okay, now that I have the two equations of motion, I set them equal to each other and solve for the time by getting all of the factors that have time in them on one side, moving everything else to the other, and I find that these two trains will pass each other at 63.158 seconds. And now that I have that time, I plug it back into both equations. You may wonder, well, why do I have to plug it into both equations? Because I always get the same answer. But it's a good sanity check. If you've made a mistake somewhere in your calculations, you will get very different positions for both trains. And remember, we're looking for the point where they're passing each other. So we're looking for the time where they're at the same position. So if for some reason you get very different answers for the position of each train, you need to go back and troubleshoot.